Hi everyone. Today we're gonna look at a topic that some people have been asking. That is, how do we know that 3 is much bigger than Graham's number, even though no one knows its exact value? So yeah, this is a question that has been asked by some people. So we all know that 3 is a very, very big number. However, no one really knows its exact value. And on the other hand, Graham's number, which is G64, same thing. We don't really know its exact value if we want to calculate all its digits in base 10. Yeah, no one really knows um, how many digits it really has. However, we can write Graham's number in this way. So in other words, we kind of know its magnitude, that is around 3 with G63 arrows, up arrows, 3. So although we don't know exactly how many digits Graham's number has, however, we know the size of Graham's number in terms of up arrow notation, which is around G63 number of up arrows. So we started with G1 with 4 arrows, and then we work our way up. So in that way, we can kind of get an idea how big Graham's number is. But for 3 is way more complicated. So in that case, how do we know 3 is much bigger than Graham's number? Especially we don't know 3 in terms of up arrows. So in order to find that, like to find out 3 is much bigger than Graham's number, we look at something called the growth rate. So one way to determine which number or sequence is bigger is to look at their growth rate. In other words, uh, there's a term for it. We can look at the fast growing hierarchy, or the FGH. So the fast growing hierarchy is a very useful tool to look at the size of, or the growth rate of big numbers or fast growing sequence in mathematics. So for Graham's number, it can be shown that its growth rate is around this thing over here. So, and then for the tree sequence, tree n, how fast does it grow? It grows approximately this fast. So we can see that this thing over here is much bigger than this. So in other words, by just looking at this two thing, we can see that the tree function grows much faster than G64. So this thing here is a bit hard to understand, but right now we just need to know this thing over here is much bigger than this over here. So in other words, this function grows much faster than this. And also, we can also use the Ackermann function to show that 3 is much bigger than Graham's number. So using the Ackermann function, it could be shown that Graham's number is around A. A stands for Ackermann function. So A 64 4. So this thing kind of means the Ackermann function iterated for 64 times. So it's kind of like A with 64 A's and 4. But for 3, it can be shown that it's much bigger than this thing over here. So A of A, again, A stands for Ackermann function. So A of 187,196 1. So this thing means the Ackermann function iterated for a of 187 196 times. So this is the number of times you have to iterate this Ackermann function compared to just 64 times for Graham's number. So we can see already clearly this number is way bigger than 64. I mean, just this number here alone, ignoring the a's, just this number is already much bigger than 64, let alone adding an a over here. So this is a much bigger number than this. And remember, this is an extremely weak lower bound for tree 3. Actually, this number here is the lower bound for a similar related sequence n4 or the nk, and this nk function is a related sequence to tree 3, except that the nk function grows much slower than the tree function. But the n4 is already much bigger than Graham's number. And that's why this number here is also used to be a lower bound for tree 3, because tree 3 is known to be much bigger than n4, and n4 is much bigger than Graham's number. So this number, although is much bigger than Graham's number, it's just a very weak, very weak lower bound for tree 3. We just know that tree 3 is bigger than this. It's kind of like Graham's number is bigger than 3. So 3 is a lower bound for Graham's number, but we know that Graham's number, of course, is way bigger than 3. And by using the fast-growing hierarchy, we can actually see that the hierarchy of functions. So the Ackermann function grows slower than the Graham's function, Gn, such as G1, G2, G3, G64, and in turn, Graham's function it grows slower than the Goodstein sequence, and this grows slower than the tree function, which is slower than the SCG function, which is slower than Busy Beaver function, which is slower than Rao's function. So using the fast-growing hierarchy, we can show that this is how the function stands in this hierarchy. So of course, it was known that the Busy Beaver function and the Rao's function, they are both uncomputable functions. That means there are no algorithms in computing the output. So in other words, since those are uncomputable, again, using this definition, we can already tell that those function grows much faster than these, because these here, they are computable functions. That means there's an algorithm in doing those functions, although it would take a very long time in computing this. But however, let's say given an infinite amount of time, you can eventually calculate, compute those numbers. Let's say if you put 10 for n, it would take a very long time, but eventually you will get there. Let's say 310. Given an infinite amount of time, eventually you can calculate that. But for this uncomputable function, there's no algorithm in doing it. So no matter what, they are uncomputable. So uncomputable will always grows faster than computable function. So that means we don't actually need to calculate those numbers, the output. And using the fast-growing hierarchy, we can see that like some numbers are bigger than the other, even though we are not calculating. We don't know its exact value. So that is how we know that some numbers are bigger than others, even though we don't know their exact values. So thank you for watching and have a nice day.